Hello, I'm Barton. I'd like to begin by saying that I'm extremely grateful to be included in Dennis's talk, as well as for the opportunity to speak at R2Con. I work with algorithms that help us make decisions, including decisions about binaries, whether a given binary is malicious or benign, for instance. I like learning more about how to represent binaries so as to make such decisions easier, and I think a lot about the differences between the highly explainable and highly predictive algorithms, as well as the trade-offs involved in using them. When Dennis mentioned he's working on the problem of soft signature matching and explained it, I was quite interested to see in how well it performed in a simple case, in a baseline. So the repository here provides the analysis that shows that for a single libc version, looking at both bytes and graph features, out of the 20 results returned, 58.5% of the time you expect to get the correct match, get the right function. I was also quite taken in with the context of this, which was to understand whether a given function you were looking at came from libc in the context of a CTF challenge, and if so, which version of libc did it come from? I wanted to help Dennis make this problem computationally tractable, and one of the ways of doing so is to look at the functions that are most distinct to a particular version of libc, allowing you to pinpoint which functions change the most. And one particular approach is to pairwise compare functions across all versions and determine which ones are most dissimilar, based, for instance, on Levenstein. Because you can pre-compute these ahead of time, you reduce the key space and only focus on the functions that are distinct for matching purposes. The repository I linked to allows you to get individual libc versions using a helper script. So if you're interested, you can do that and look at RSI2 outputs to work with a similar comparison. I also wanted to reach into my toolbox and see if there was anything else I could do or anything I could use that would allow me to compare two functions. And one method in particular that will temporarily take us away from signatures, but I promise I'll bring us back, is a method called SAFE, or self-attentive function embedding for binary similarity. The authors of this paper were gracious enough to publish the code, both in TensorFlow and from Facebook Research and PyTorch, and the weights, or rather the pre-trained embedding that resulted from their experiments. So if you're watching this, thank you. The method itself is quite similar to a lot of natural language methods. In this case, it's a recurrent neural network, GRU, with an attention mechanism. And similar to word2vec, instruction2vec turns something that's not a vector into a vector. In this case, the inputs are the assembly instructions from a disassembled function. And of course, Rodari2 is used to perform this disassembly of the inputs. The actual embeddings are trained given the semantically similar and dissimilar function next to each example, and then evaluated in multiple tasks that I'll list shortly. The model itself is trained in such a way so as to produce an embedding vector. And then for any two functions, you can use the resulting vectors to compute the distance between them, in this case using cosine similarity. And then the distance metric is interesting in that it allows you to compare two functions that may appear dissimilar, not necessarily, but may, in terms of not only how they look, but in particular in terms of the actual functionality, the actual actions that these functions perform. Here is the example, a visual illustration of the concept. You start with the instructions and you end up with numbers, just the numbers. And then the tasks themselves included comparison of AMD 64 and ARM, function search, which is relevant to us, vulnerability search, and then also semantic classification, which is detecting whether a function contained encryption functions found in Windows malware. Another illustration shows you what cosine similarity actually is, and then for two functions illustrates that you can compute the similarity between them and use that as a way of comparing them and finding matches. And so for top 20 nearest functions on task 2, which is function search, precision was 77%, recall was 36%, and increased as you increase the number of results, of course. And then another metric used was to take ordering into account. Obviously, we want the right matches to be first, and so NDCG metric was 80%. Finally, performance-wise, this method performed quite well. And so the authors cite 1 second to compute embeddings for 1,000 disassembled functions. For reference, libc would be about 2,400, and so having that plus the time it takes to disassemble is how long it takes to compute the embeddings, and then finally the comparisons themselves would also take up time. Now, this is a very abstract method. It is not very explainable, even though attention can direct your gaze to a specific portion of the binary that is meaningful in this classification or comparison. But what's the right balance between this and a method that is more straightforward? Also, given that we are in Rodari 2 land and we want to include things in tree, can we actually do it in a way that is compatible with Rodari 2? Can we use something like the accelerated linear algebra compiler or TF compile to compile something like SAVE and link it into Rodari 2? And then once you do that, what is the right user experience for combining this and the other methods? Do we add it as a column with its own score and try to explain what it means? How do we account for retraining of this model? And also, finally, to bring it back to signatures, can a similar approach of taking something like a signature itself as an input over a large number of versions of libc be effective enough at producing an embedding that can act as a more meaningful, faster semantic alternative to Levenstein? Lastly, I'll link to the question of using attention on its own to determine such things in other contexts. In particular, the paper is called Attention is All You Need. This is the foundational paper that spawned quite a lot of derivative work in the space of natural language processing. A lot of the models you see today rely on this architecture. And so a further research direction I would like to pursue is to see what an embedding on a signature looks like. Can we capture that intuition that Dennis has that these two binaries sort of look the same? A word of caution is that sometimes simple is best. So what you see is that up until those versions listed, you could crash TensorFlow and lead to denial of service attack if you chose to use this in production to classify your binaries. So you could pass a string where a float 16 was expected and then lose your process. So a straightforward method has less complexity and less moving pieces, and so sometimes it's best to stick to simple things. Finally, I'd like to encourage you to reach out if you want to talk about these and other concepts at the conference and outside. And at this point, we'd like to open it up for questions.